Good morning. Today is the last class on cycloaddition. Okay, and in this class we will be talking about 2 plus 2 plus 2 cycloaddition reaction, right. In standard organic chemistry, this is not given much importance, but as far as the heterocyclic is concerned, this is a very important class of reaction, very important class. Okay. Why it is so important? Primarily because the functional group compatibility of these reactions are very versatile. In, let us say, under the acidic conditions or basic conditions, the functional groups that are not reacting may be affected, but in cycloaddition reactions are so chemoselective, the reaction will take place in the part of the pi bonds or I should say triple bonds. And this reaction is so useful. In fact, almost every year we are having a review on this particular subject. Okay. And the latest one you will find in chemical reviews. It's in the portion called ASAP, as soon as possible. The page number is not given, and by saying 2 plus 2 plus 2 cycloaddition, I think all of you have understood what I am going to say. It is not related to the olefins, but mostly related to the alkynes. Okay. The earliest one all of us know. The earliest one is the trimerization of acetylene, and this was reported in 1866 by a scientist called Bartholomew, and the reaction was reported to take place at a very high temperature. What was the temperature? The temperature not 600 degree, it is around 400 degree. Well, maybe I do not know, you may have seen somewhere, but wherever I have seen, it says it is 400 degree centigrade, and that was for the preparation of, many of you know, for the benzene from acetylene. That is a standard reactions, but people never used it. It was of importance with respect to the science only. Acetylene can be converted to an aromatic compound just by heating. Then actually the first landmark was done in 1949. That was by a scientist known as Reppe. Okay, scientist Reppe, and what he could do the same kind of reactions. Same kind of reactions means alkynes. This is extended these alkynes and to substituted alkynes. Okay, and what else? And this he could use a transition metal. I think transition metal, and that was actually nickel cord, and at the temperature around 60 degree centigrade. The reaction products, of course, I should write here benzene derivatives. All of us understand why benzene derivatives, because it could be a mixture of the products, right? Mixture of the products. Normally, if you have a monosubstituted alkynes, you are likely to get 1, 2, 4 substituted benzene derivatives. Occasionally, you will get 1, 3, 6, that is symmetrical one trisubstituted compounds, but mostly 1, 2 and 4 substituted benzene derivatives. But what is remarkable about the Reppe's experiment, you can see here, by the use of transition metal you can lower down the temperature to 60 degree centigrade. Okay. There are problems with this, but at least the reaction is manageable under laboratory condition. That was the advantage of this Reppe's. Okay. But then there are other problems, of course, there are other modifications, other developments in this area, but in our context it should be extendable to heterocycles, right. So, that means what we need, we need an alkyne and possibly a nitrile. So, if you can do these 2 plus 2 cycloaddition reactions, you are likely to get this substituted pyridine. So, that is, so this is one of the, that means ways one can do this, and in this class what we will talk about we will talk about this sort of cycloaddition, that where you will have one nitrogen somewhere or oxygen somewhere, so that you can make the heterocycles. Okay. And then what else we will see? We will see the reaction conditions under which the kind of the catalyst what we can use. That is then what else? Then the kind of the substrates that should be available, and then what are the products that can be obtainable from these sort of reactions. But to begin with, I mean, there are tricks. You can get all kinds of compounds like carbazole, you can get phthalates, you can get bisphthalates, all kinds of things. But without doing this heterocyclic 2 plus 2 plus 2, depending on the positions of the heteroatom, you can make all kinds of heterocycles, all kinds of natural products, but mostly 2 plus 2 plus 2 cycloaddition reaction in heterocyclic chemistry is limited to pyridine synthesis, substituted pyridine synthesis, and there is a class of molecule called 2 pyridones, that means 2-oxo-pyridine you can say. Okay. So, that means these reactions are useful only for those special categories, and then there are cases you can bypass it to make heterocycles without involving a heteroatom during in the skeleton, means where component is having a heteroatom. Okay, component means reacting components, means tri-alkynes component. Mechanistically, let us say what one can expect if you have metals, if you have 2 alkynes, one can just simply think about, right, something like this. If you have metal here, normally the metal node is metal 0, usually low valent metals, Then we will talk about what kind of metals are used. So, I think you can all basically, and insertion of the metal, oxidative insertion into this alkyne system, and then if you have something like this, that means this nitrile. I mean, there are ways to look at, but one of these way one can see that as if there is a kind of a Diels-Solder kind of reactions, with this like this, right. So, then what else you can think about now, and this is one of the very simple mechanism or simplified mechanism, and the next basically what you can see here, you can just if you have known the reaction called cheletropic reactions, right. So, cheletropic reactions, so that are basically retro-Diels-Solder reactions. So, sort of that means once again the metal comes out. So, it is a catalytic process, right. So, metal should come out, and what you will be ending up is nothing but a pyridine derivative. Okay. And so, this is the mechanism, you can just mentally work it out, and this but as you will find, this alignment of the acrylonitrile is important to give particular regioisomer, that we will talk about, but in most cases these reactions are not very regioselective, Okay. I think one can see different possibilities. For example, if you have just intermolecular version, means all the 3 alkyne components are separate molecules, then you have all kinds of the possibilities. If it is substituted, you will have all isomers. Okay. For example, if you have 3 different alkynes, one is disubstituted, another is a disubstituted, another is a monosubstituted, then how many aromatic isomers are possible arising out of these 2 plus 2 plus 2 cycloaddition reaction? Guess? Do you understand what my question? If the alkyne compounds are different, they are all substituted, one of them is let us say monosubstituted, then how many isomers of benzene derivative can you expect? Well, once upon a time I counted, it is more than 30, more than 30. So, that is the serious problem. That is the reason why this kind of reaction was not very popular either in the aromatic chemistry or in heterocyclic chemistry. Okay. So, one can do, so you can just have a semi intramolecular version. Semi intramolecular version means like say you have 2 components attached together in one particular molecule. Okay. Then you can have one alkyne. So, this is a kind of semi, that means 2 are bound to a place and the other is free, then chances of, that means and what you will get? You will get the benzene derivative here and this. So, this could be a substituent, this could be a heteroatom, all kinds of things. Okay. If it is X in a heteroatom, of course, you know what it is. So, officially we can say that we have made a heterocyclic molecule, although what we have done really, we have done basically we have constructed the benzene moiety. So, it is not truly a heterocyclic construction, but end product is a heterocyclic molecule. Well, X could be tethered atom, I think tethered atom or tethering atom maybe. I think you understand the meaning, right? It is basically a temporary atom which has been used to join or combine 2 units together, and then at the end of the reactions that is removed. It is not really a protecting group, but it is basically the purpose of these atoms are to bring 2 reactants together in covalent manner. Okay. And now, the same kind of reactions, if you let us say instead of the alkyne, if you take the corresponding nitrile. So, what you will be getting? You will be getting the pyridine derivative. You will be getting the pyridine derivative, right. So, now this is actually truly heterocyclic constructions, truly heterocyclic constructions. So, similarly you will have all kinds of the probabilities. I mean you have all different varieties. In this case we have placed the nitrogen in the single alkyne portion. Now, one can think about the same thing in a different manner. Let me say one is alkyne, then other is let us say cyanide here, and then this one is a plain alkyne. So, once again you will get a pyridine derivative here X and R, and then of course, the other isomers are possible in this case. So, you will have N here, R could be this is not, R could be here X and X. So, these are all different possibilities, different possibilities. What are the other possibilities? Other possibilities of course. So, this is nowadays semi kind of intramolecular version. The other possibilities could be just basically a simple other possibilities could be again a triple bond, right. Then you put one more tether, or you can just then an alkyne. So, obviously the reaction would give you a benzene derivative here, a tethered atom on this side and tethered atom on this side. And this is what is very successful in organic chemistry, simply because it is intermolecular versions. All these atoms or the reacting components are in right place. So, yields are good and success rate is high. Now, so if you just modify this version and you can convert it into basically heterocyclic model. Okay. That means same thing X and then triple bond, then one more X and then and this let us say the end is an acrylonitrile. So, then eventually you will get the same thing as before and same thing as before. Here now in the place of carbon you have a heteroatom, that is it. So, but what next? Okay, next is to see how they are useful and what are the molecules we can make, number one. Number 2, that is very important, about the studying about the catalyst, what sort of catalysts should be used. Okay. These reactions are limited to a certain kind of catalyst. The one that is commonly used, this is metal here, metal complexes, is the cobalt complexes. That is first thing, this the most popular one. The next one is rhodium, and occasionally you will find ruthenium. Okay, so I would say the first two is more important than the third one. Okay. And then of course, there are other minor ones, like say many times you will see the nickel like Repp's catalyst, nickel these days iron catalyst, iron iodide and zinc combinations, and people are also using iridium. Reason being, iridium has a high propensity to induce asymmetric induction. So, iridium and occasionally titanium has been used, and there are cases like palladium, and one more maybe at the moment I am not sure, there is a metal tantalum, it may be a wrong mistake, but there is a possibility I have seen somewhere. Okay. So, but at the moment I think we should concentrate on cobalt and rhodium, and then in certain cases in some of the specialized atoms. Okay. And what are the rhodium cobalt was actually first introduced, I should not say first, but it was largely used by a very well known scientist known as K.P.C. Volhard. Okay. And he is very famous, and throughout his career he had been working only on this area 2+2+2 cycloaddition reactions, and occasionally had to, but most of the times he has produced the carbocycles, and he has developed very elegant synthesis of steroids and alkaloids. I will give you 1 or 2 examples from the alkaloids. Okay. And mechanistically, okay, just what are the differences? The differences, first of all, when you go from cobalt to rhodium to ruthenium, you will see the mechanism is very similar for cobalt and rhodium, but as you go to ruthenium, this is a different kind of. Okay. If you go back to the mechanism, you will see that we have made a metallocyclopentadiene, right, and then it has undergone sort of an addition, but some people say that acrylonitrile undergoes insertion between metal and the carbon through this to form a 7-membered ring systems, and then some people say no, there is no something like this, that a Diels-Alder intermediate of this metallocyclopentadiene or something, they straightway make this hexene ring. So, all different mechanistic proposals are there, but what is accepted about this cobalt is that this it involves metallocyclopentadienes. Okay. And now let us look at, I mean, without doing heterocyclic formations, we can also make heterocycles, means without constructing the heterocyclic ring we can make heterocycles if you have a heteroatom somewhere else. Okay. That is the example, let us say we will give you for example, here is a big structure, I will just show you. It is a benzene derivative here, then you have a side chain, ortho side chain with alkyne, and then you have another alkyne on this side. Then what you see, backbone is now not backbone, I should say this substituents is having a lactone moiety here. Then I mean, so one more alkyne, then TBS, tributyl, sorry, not tributyl, tertiary butyl dimethyl silyl. Okay. And then you have a double bond here and a methoxy here, here methyl group. Now, what you see, I think the way I have written it is pretty easy to understand what is going to happen, right. So, it first will have basically you will get a new benzene ring, right. This one would form a new benzene ring, and then what else? This lactone here now, and this then OB and OTBS. So, the connection, okay. So, how did it form? Basically, you have to identify the alkyne portions. So, this alkyne gets the connected chair, okay, and as if that means you start from anywhere, let us say from normally what you do, you start from a terminal, okay. So, 1, 2, 3, 4, 5, 6. So, that means this should be connected here and this should be connected here. So, you get basically 3 new bonds here, and then of course, 3 double and triple bonds become the double bond, that is it. So, and then the rest of the things remains as it is, and this. So, what you see here, we have constructed basically benzene ring, but net result is a heterocyclic molecule. That means, what we call this portion is basically phthalide or benzoisofuranone. And what is to be noted here? Anything that okay, the tertiary butyl group survives, that silyl group survives, and what else do you see? What else do you see? There is something pretty interesting here. Lactone ring survives, okay. Anything else? That you have to remember. See, there was a possibility that double bond could also be involved in the cycloaddition reactions. So, it did not. That means, these triple bonds are more reactive than the not really. Actually, here also you have to take care of the geometry important. Geometry also is important. I mean, you have to just sit down and see whether that would geometrically permit or not. Okay. So, it is very difficult to pinpoint whether double bond is more reactive, but triple bond is more, but this sort of reactions I would say more successful with the triple bonded compounds, okay, alkynes. And let me take you to okay, but what I missed then, I missed what is the catalyst. So, when I say what is the catalyst, then you have to think about cobalt or rhodium, and when it comes to rhodium, obviously all of us know what it is, right. Rhodium Cl and within bracket something PPH3 whole 3. What is it? Wilkinson catalyst. So, that is the beauty, Wilkinson catalyst. That means, Wilkinson catalyst also, I mean many of us only know that Wilkinson catalyst is useful for hydrogenation, and occasionally they are also useful for in standard organic chemistry useful for reverse deformylation, actually called decarbonylation. And now you see here it also indicates it is very useful, and there are plenty of examples where the Wilkinson's catalyst has been used for 2+2+2 cycloaddition reactions. One more example maybe I will give you. So, here you see here advantage. What is the advantage? Rhodium, and number 2 is okay. Number 2 is an intramolecular. So, intramolecular version is more successful. Now, let us look at one more example where it is semi intramolecular. Like say, if you have a benzene derivative with alkyne and then nitrogen substitution with tosyl group, and then you have another. So, what you have by writing this structure, what you can see, we have actually jotted down all these alkyl portions. We can identify the 3 different alkyl component. Now, what you have to do? You have to choose a catalyst. So, obviously, the cobalt one is more preferable because that has been more successful, but within rhodium this is Wilkinson is more readily available, one can just buy it. Okay. So, do that, and what you will find just in toluene, the reaction is carried out in toluene and just reflux, sorry, room temperature, just room temperature. So, mind it, now if you go back to the Barthelot's experiment, it was 400, Repe's was 60, then actually the previous one was only 40 degrees centigrade, that is basically dichloromethane boiling point, and now you see the room temperature. So, I mean, there is a significant improvement as far as the energy is concerned, convenience is concerned, the scaling up of a reaction is concerned. Okay. And I guess if you sit down, you will be able to write the structure. So, what should be the structure and what is the product? It is a carbazole. It is a carbazole and tosyl. So, this benzene ring is this one and this methoxy here, and then carbon. Okay, this is now. So, phenyl, nitrogen, and this one is this triple bond, right. So, I think methoxy should be somewhere here, right. Methoxy should be here, or okay. Benzene, then this is a tosyl group. Oh, sorry, this should be phenyl, right. This should be nitrogen, phenyl, and this comes from benzene, and this one is this should be methyl, right. This should be methyl, and this one is methoxy. Okay. So, this one is methoxy, this one is methoxy, this is methyl, and this. So, that means you see here, this is nice way of looking at the reaction. That means you can, but essentially what you did, you actually constructed it's not a truly a heterocyclic construction. We have constructed only the benzene ring, but just by placing heteroatom here and there, we have come up with the formation of a heterocyclic molecule. Okay. And so, then how to make heterocyclic molecule? How to okay, and what should be the approach? In truly intermolecular reactions are very few, as I said, either semi intramolecular or totally intramolecular reactions. Now, you want to think about the heterocyclic constructions. So, obviously, your component, one of the components should be the commonest one is acrylonitrile, and we have already seen, that means if you have a substrate of this kind, that means it is a semi intramolecular, and then react with an acrylonitrile, and acrylonitrile. So, what we have already seen before, we can get pyridine derivative, but the same substrate if you use with isocyanate. So, what you will be getting? You will be getting again a 6-membered ring, right. Sorry, this is CH2, this is CH2, this is CH2 X. So, it is easier to remember. Okay, X. Now, there is CH2 double bond, sorry, and now what? Double bond should be placed here and here, and ketone, then R. So, what you will be getting? You will be getting pyridone, right? A nitrogen somewhere here. So, nitrogen. So, that means it is the carbon double, that imine portion is reacting with this or participating. Okay. You have to make out here, you have to just understand that the one that is less polarized or which is more covalent in nature undergoes this sort of reactions. Okay. But there are cases, but there are not many though. There are cases where you can also use carbon dioxide. In the case of carbon dioxide, any of these double bonds would be reacting, that is not at all a problem. So, then what is the other possibilities? You can take isothiocyanate, you can take carbon disulfide, or that means one can also think about these carbon disulfides, then all people can think about this RNC double bond S, Okay. So, all these possibilities are there, but among all these possibilities there are two of which are more prevalent. Which are those? One is the pyridine formation, another is the pyridone formation, two pyridone formations. Okay. And we will just have a few examples, basically how to make pyridine derivatives, and then what are the different kinds of the catalyst which could be, I mean there are a wide variety of catalysts, okay, n number of catalysts. You can just modify the catalyst with a particular ligand, it works, and without a particular ligand it does not work. So, there are all different kinds of varieties, and sometimes these ligands are such simple ones which are not normally thought about. Okay. Let us say the example I have a kind of reactions again is semi ones. So, in the semi ones, what is semi intramolecular ones, what you do, you take say dialkynes, right, or alpha omega alkynes, and then you think about acrylonitrile. Okay. So, in principle this should have worked at the room temperature, but when you increase the substituents, the temperature has to be increased, and in this case the catalyst that has been used is okay. In this case not more polarizable, I should say more covalent in nature, more covalent. Which one is more covalent? I suppose, yes. So, in this case actually what you are expected to get of this kind, where no, actually in this case the carbon double bonded sulfur has reacted, and this imine portion right. Okay. And so, this is called thiopyramines, again that too under specific conditions. Okay. So, these are not very, that is the reason I did not talk about, this is not, they are all isolated only examples. Okay. So, now we have a substrate here ready for 2 plus 2 plus 2 cycloaddition reactions. Now, you have to choose catalyst. Of course, the first one should be the cobalt one, the cobalt is more popular. So, what you use, that all of you know, Cp and then cobalt, and then what? No, carbon monoxide, not whole 2. Okay, that is actually more popular one. The more popular one, Cp, cobalt, and then carbon monoxide whole 2, right. But in the one that has been used in this case is something like DMFU. It is nothing but it is a very simple compound, dimethyl fumarate. Dimethyl fumarate, all of you know, I guess, right. This is dimethyl fumarate. That is what I am telling. That is ligand could be made of different kinds. The commonest one is CpCO, Cp cobalt, and then carbonyl twice. That is the commonest one, that is actually exclusively used by the KPC borer. Okay. But in this particular example, and this has been more successful, and the reaction is carried out at 110 degree centigrade. So, what do you get now? Of course, you get now di as a compound or the pyridine derivatives, nitrogen R2 here, R1, then tosylate, and then CH2 is N. So, you have all kinds of these and I have more examples. I think I will skip some of them, and the next category of examples what I have here is very similar to this one. That means, it is a bicyclic pyridine derivative, right. And the next example what I have, this nitrogen is within the first component, and the third one, second one is just a plain alkyne. In that case, the example, that is the Cp CO, that is I think cobalt, and then this is Wohler's reagent that has been used. So, I mean I will not write, very similar substrate. In this case, nitrogen is on the left hand side, and this one is a plain alkyne, and so one would be able to get this kind of molecule here, R1 and R2. R1 R2 comes from, that means one can write very quickly R1 R2 comes from this alkyne, and the pyridine nitrogen comes from the tethered diene portion. Okay. So, and this in this case temperature is not mentioned, in temperature is mentioned. So, likewise we will have more examples maybe towards the end of the class. Let me tell you one more example which is been developed by C. Wohler with a target to synthesize a natural products. Many of you probably would know this name, but you do not know the structure. LSD, how many of you know? How many of you know LSD? Okay, what is the full form of LSD? I thought all IITians know. LSD, lysergic acid diethylamide. Okay, it is a molecule of this kind. It is an indole, you can look at as an indole derivative, and then so best I will write just if you just write down this name LSD in the Wikipedia or Google, you will find the name. Okay, it is pretty well known among those. It is basically used in the, by the drug addicts. Okay. So, and the structure is like this. So, you will have it basically in an amide moiety, diethylamide moiety. So, this has been synthesized by many routes, or one of the possible routes could be, you can see here, one of the possible routes is that you have a pyridine moiety here on your left, and to examine whether this 2 plus 2 cycloaddition could be a possibility. So, C. Wohler, what he had done, he had taken a indole derivative, and had taken an indole derivative here, and cyanide, of course, what else you need, if you just alkyne, and what else, one more alkyne, that means this is somewhat like a semi again tethered, or the two components are joined together, and the third one is an alkyne, then TMS, and this OH. So, if you write, that means if you take this here 1, 2, 3, 4, 5, 6. So, you have the 6 atoms would be reacting, and in this case the example is Cp again, then cobalt and then carbonyl, 2 of them, but mind it here this one equivalent was needed, and eventually he could get this structure very similar to what is there for LSD, this one, and it is not exactly the LSD. What you will get is this without the silicon here. By the way, silicon is knocked out during this reaction, So, what you get is the entire skeleton has been assembled by just one single step, and mind it, there is no protection for the OH group, there is no protection for the nitrogen. So, you can get to this. See, we have been working on the heterocyclic chemistry, alkaloids for a long time, but most cases what we do, we protect the nitrogen and do all kinds of reactions. Otherwise, and then we end up in difficulties having to in having this protecting group to be removed. Okay, so all kinds of problem, but without using protecting group, if you can make a synthesis, that would be definitely better than the one that one can think of. Okay, but then this has been the problem, and it was done in orthoxylene, that means at higher temperature higher than 130 degree centigrade. At the same time it was exposed to light. Okay. And if you know a little bit of this reaction mechanism of the organometallics, probably you will become know why the light is used here. Anybody? Light? Very good, very good. Activate the cobalt complex. It actually loses the carbon monoxide. Then these alkynes and alkenes can undergo coordinations on this cobalt surface. Okay. So, that is sometimes required, sometimes it is not required depending on the situation, but in this okay, even sometimes simple heating also activates the cobalt, and we will see more, in fact more kinds of the catalyst where carbonyl is not there. Okay, a very similar catalyst, but that means for the carbonyl complex there is a problem, you have to activate it by removing the carbonyl. So, if you have a pre-catalyst so which will have other than carbonyl, which is easy to leave cobalt metal, that also could be useful. Okay. And one of them is basically the diethylene complex. In the place of carbonyl, if you have diethylene complex, that also would serve the catalyst for this sort of reactions. And in fact, I will not give you the example, it will take time. So, the next example of the on this lysergic acid synthesis has used this cobalt ethylene complex, and to the extent of 2.5%, means in this one equivalent of cobalt catalyst has been used, pretty expensive. And the other examples very similar to that. Other example it was nothing, it is a new catalyst, as the cobalt here and this ethylene complex, and the percentage used is 2.5 mole percent, 2.5 mole percent has been used. The substrate is a little different though, in this case, in the case here all the three triple bonds are in one single substrate. That means, this is basically fully intramolecular, substrate. I will not write the structure. Basically, what you do, you join all of these three alkynes together. So, in that case, actually the percentage of the cobalt complex is much less. And if you are interested, I can give you sometime later, but okay. So, what next? There are other examples where you will have this nickel catalyst, titanium catalyst, maybe we will just skip them, but what I will just show you one of these important examples of the two pyridone synthesis, and the one that is pretty well known here is you take diethyl acetylene and then phenyl isocyanate and then a catalyst. In this case the catalyst was nickel cod and the percentage nickel cod 3 mole %. So, I should write here the 3 mole % nickel cod and then 3 mole % of SIPR. I will tell you what it is. It is a NHC. It is an NHC. NHC, I think some of you know, many of you know, I guess, right? NHC, right? Nitrogen heterocyclic carbenes. Okay, so it's NHC, and the reaction can be carried out at room temperature, and the reaction product, of course, all of you can guess, and sorry, single bond, this is phenyl. So, you get the basically 2 pyridone derivative. So, carbon double bond nitrogen, which is more covalent in nature, that participates in the reaction, eventually you get to this compound. Okay. What else to be known? Phenyl isocyanate. Phenyl isocyanate, where do you get? It is a commercially available, but if you cannot get it, then you have to make it. How do you make it? Phenyl isocyanate, you have to also know this. Phenyl isocyanate, how do you make phenyl isocyanate? Okay, we do not make it though. We know we how to write from Hofmann degradation, but we do not isolate it from there, right? It is an intermediate, but if you want to isolate an isocyanate, you have to use, I mean there are all kinds of, you can do the reductive carbonylation of nitrobenzene. Okay, under again a transition metal under catalyst, you can reduce the nitrobenzene to nitrane, and then carbonyl undergoes insertion to form this nitro. Okay. Then if you have a corresponding urea derivative, you can do the dehydration, and but in chemical laboratory there is a very useful reaction, important reaction. You take the carboxylic acid and then you work out the mechanism. Maybe I will see next time, tomorrow. Tomorrow Professor Zekaria would not take class, so I will take the class depending on the situation either here or in the department. Okay. And if I am ready, then I will take the class here, otherwise I will take the class in the department. So, you work out this problem, and then this is a reagent. I think I will be able to write though, long time before I did this, azido diphenyl phosphonate, hopefully right 1, 2, 3, 4, 5, yes. See, in one shot you will get this isocyanate. Okay. It is a very useful reaction, hopefully. I think I am almost correct, and so what else? There is a compound I said, right, that NHC. What is NHC? NHC again in this case I said SIPR. I stands for actually imidazole. So, it will have this imidazole, right, and then isopropyl here, and then IN isopropyl, and sorry, not IN isopropyl, it is actually benzene isopropyl, sorry, diisopropyl. Benzene and benzene will have the diisopropyl groups here and there, and the note from where I have taken this example, it does not give the double bond here, but I presume there should be a double bond, there could be a double bond. Okay. So, I have to go to the original literature. There are NHCs where we will have the double bond and without double bonds, all kinds. Okay. So, this is actually it is a symmetrical one. So, that is the reason why it is symmetric SIPR, and sometimes also this this actually S stands for the S configuration, S configurations, S configuration of this aryl system. Okay. So, but this example just to show you that it can NHC can be also be a useful ligand. And what else? I think we have talked about many important things here. Maybe we have missed one or two points. Let me see. Okay, yes, this is a very important one. Say if the reaction does not take place, what do you do? Let us this is not a heterocyclic example, but let us say we have an alkyne here, tethered alkyne, and then let us say I write here E is an ester here, ester, simple ester, and then alkyne. Let us say you want to do 2+2 cycloaddition reactions here. Okay. 2+2 cycloaddition reaction. The conventional Wilkinson catalyst does not work. Okay. The conventional Vollard catalyst, that means the carbonyl complex does not work, ethylene complex does not work. So, what can you do? So, that means basically you have to activate the alkynes, right. So, and in this case mind it, one of them is not an alkyne. What is it? Alkene, right. So, you have to have a real active catalyst. So, how do you make this catalyst active? That means you increase the ionic character, So, this Wilkinson catalyst, which is basically rhodium based catalyst, you have COD and then 2, and to make in Wilkinson you had chlorine to make it ionic in nature. So, what you have to do? You have to basically change the counter anion. So, what counter anion in organometallics do you do? Use perchlorate. One of them is perchlorate, the other is tetrafluoride. So, that is it, and you require only 5 mole percent, and you get, then of course, there is a ligand, there is a separate ligand here, that is for other reason. All of us know that BiNAP is a famous ligand, phosphorus based ligand, and this is used just to explore some other thing, because there is an asymmetric version. Okay. And there are you can make use of this sort of ligand. So, that there are examples where you can make bi-aryls, and in which one of them is heterocyclic in optically active form, okay, provided your BiNAP is optically active. But any case, in this case, so you can smoothly make the corresponding benzene derivative. So, that means the choice of catalyst is important, and you have all different varieties of the catalyst, all different varieties of the ligand, NHC2 dimethyl fumarate, all kinds of things. Okay. And so, there are examples where you can use cyanogens, many of you know. Cyanogens is, what is that? Cyanogen is 2 cyano groups together, just like it is a pseudo halogen, right, it is a pseudo halogen. So, that means you have 2 cyanogens. So, that means acetonitrile is one of the components in 2+2+2, but there are also examples where you can use cyanogens. Okay. And so, let us see summary. What is the summary? Summary: 2+2+2 cycloadditions reactions are limited to pyridine synthesis and pyridone synthesis, right, and occasionally they can be used to make other alkaloids, provided it contains a benzene ring, where you construct the benzene ring, right. Third important point, the cobalt and rhodiums are the more useful ones. Okay. Cobalt has 2 variety, carbonyl 2 and then ethylene 2. Okay. And then other points could be the rhodium. Where do you use rhodium? Well, if actually one should go for rhodium first, readily available, but it is apparently it is less reactive than the corresponding cobalt. Okay. But rhodium can be made reactive by changing the counter ion. And also you have to keep it in mind, the rhodium based catalysts have been used for totally intramolecular reactions. When you have all these things are in one molecule, then it is easier to carry out with rhodium catalyst. And all of us understands that the region selectivity problem can be solved by tethering all these trialkene in one molecule. That means, if you make these reactions intramolecular inversions. Okay. Asymmetric versions are there, but I should say it is not very popular. It is not very popular, but people are still exploring to make all these reactions asymmetric. Okay. When you say asymmetric, means actually not traditionally you are generating the chiral centers. It is basically the chiral axis you are generating. That means, bi-aryls can be made from this sort of molecules. Okay. And what else? I think we have given you most of the important aspects. As I said before, it is not very popular with carbon disulfide as one of the reacting component, and or these 5 isocyanates or carbon dioxide, but there are examples. There are examples you will find which can be which can involve alene systems. That means, the just isolated alkenes are not very reactive, but if you have an alene part, just simple alene, it can also participate in the 2+2+2 cycloaddition reactions. Okay. That means, 2 are the alkynes and third one is the alene, that is also a possibility. There are examples where you can make use of, and I think that is all we have. Other than this, I guess we have talked most of the important aspects of the 2+2+2, and I think we have taken care of most of the important things.